Thank you very much. It's a great pleasure for me to be here among all the new friends and colleagues. So for the next 30 minutes, I'm supposed to talk about a recent project. So the title is Dirac cohomology and theta correspondence for complex reductive dual pairs. And that's a joint work with Gang Liu and Salah Mehdi, both from the University of Leuven. And here is the plan of my talk. So in the first part, I will explain what the theta correspondence is. And then what the Dirac cohomology is. Pavle has already said a few words about Dirac operators. And then in the last part, some results concerning their connections. Okay, so let me start with the first part. And let me recall some facts about classical invariant theory. So in classical invariant theory, we start with a group G. And then we have a nice standard representation of G on a vector space V. And we are interested, we consider the polynomial algebra for V. And we are interested for the dual space. And we want to determine polynomials which are invariant by the action of G. For example, one can consider the orthogonal group of n by n matrices acting by matrix multiplication on Rn. And then, of course, G will act on the polynomials defined over V by left translation. And the question we want to decompose this action. And now a helpful trick is the following one. Trick. I don't know if we can call it trick. So we want to find a partner for the group G, another group or some algebra which will act on V, and the two actions will commute with each other. For example, for this case, we can obtain almost for free two differential operators if you want. Let's call it E. So just the standard quadratic form, which of course is preserved by the action of the orthogonal group. And the Laplacian. The Laplacian which again is preserved by the action of O1. And then let's call H just the bracket of E and F, which is another element. On C of V, yes, by left translations, yes. And then these three guys form an SL2 triplet. And the action, they act, of course, on this polynomial space, and the action of G and the action of SL2 commute with each other. So we can obtain a decomposition of this space as a G SL2 module. And the classical invariant theory says that this decomposition is given by, where is it? And then we have the following theorem, which says that for Rn, we have the following nice decomposition. So this is the space of harmonic polynomials of degree D, and G acts here. And this is the irreducible lowest weight representation of SL2 with this lowest weight. And D runs over the positive integers. So this guy sometimes may be 0. If not, it's irreducible. And for different D, because of dimension reasons, all these irreducible G modules will be inequivalent. So in other words, in some sense, for every irreducible G representation of for every irreducible representation of G, we attached an irreducible representation of SL2. And if there is some irreducible representation which does not appear here, then we can say that we attach the 0 representation. So in some sense, we have a duality between representations of the orthogonal group and representations of SL2. And now let me introduce what we call a theta correspondence, which is, if you want, a generalization of this idea. So theta correspondence. So we start with a complex, with a finite dimensional complex symplectic vector space. So this is finite dimensional complex and symplectic. And then G will be the corresponding symplectic group. And in G, we fix two closed subgroups, and we will say that G1 and G2 is a reductive dual pair. So reductive dual pair if the following two conditions apply. So the centralizer of G1 in G is G2 and vice versa. And moreover, G1 and G2 act on W reductively. Okay, and if W does not contain any G1 times G2 invariant subspace, we say that this dual pair is reductive. Now, for our case, where G1 and G2 are complex groups, so there are two types. There are two types of irreducible reductive dual pairs. Namely, either G1 is an orthogonal group and G2 is a symplectic group, or G1 is GLM C and G2 is GLN C. So these are up to equivalence. These are the only possibilities for complex reductive dual pairs. Excuse me? No, because yes, you can consider it as a, yeah, because SL2 actually is a symplectic Lie algebra, if you want. Yes, if you want, yes. There are some exceptional isomorphisms for low dimensional, for the low dimensional case. Yes, if you want. Okay. And now from Stone von Neumann theorem, one obtains a representation for the symplectic group known as the metaplectic representation of the symplectic group, and we set omega I to be the set of all the irreducible representations of GI such that they appear as quotients of the metaplectic representation. And I is 1 and 2. So we take all the irreducible representations of G1 such that this space is non-zero. And the same for G2. And then the following relation then the following relation defines a bijective correspondence from omega 1 to omega 2. And this correspondence is known as theta correspondence. So in other words, to every irreducible representation of G1, we attach an irreducible representation of G2. If the irreducible representation of G1 belongs here, I mean, belongs to omega 1, then we just attach P2. If P1 is not, if the irreducible representation of G1 is not in omega 1, we just attach 0. So for every irreducible representation of G1, we obtain an irreducible representation of G2. This is what we call a theta correspondence, or how duality, or dual correspondence. And in this case, when P1 or P2 are sent to non-zero representations, we say that they appear in the theta correspondence. Okay, and now let me say a few words about Dirac operator. Dirac cohomology. So G is a complex Lie algebra denoted by this bilinear form, the Killing form, semi-simple. And then consider a Cartan decomposition for G and construct the Clifford algebra of P and a space of spinors for this Clifford algebra. So in other words, this is just a simple Clifford module for this Clifford algebra. And then K, I mean, this space S can be equipped with an action of the Lie algebra K. We have a composition of Lie algebra morphisms. So at the same time, S has an action of the Clifford algebra and of this Lie algebra. And then the Dirac operator in this context So if you want, what Pavle considered is, I mean, K was the whole Lie algebra. There was no P. Am I correct? No. And so, excuse me? Yes. So, and we define the algebraic Dirac operator to be, so we take a G module and we define the algebraic Dirac operator to be the operator given by this formula which acts on this space. So this is a linear operator acting here, which is given by this formula where Zi is an orthonormal basis for P. And then this operator, first of all, is K equivariant. And then it has a nice, so it satisfies a nice formula for its square. So it's somehow an algebraic Laplacian, which is very crucial for the results concerning this operator. Okay. And then we can define the so-called Dirac cohomology of the G module X to be the following quotient. So this is the Dirac cohomology. Of X. And of course, this is a K module for the Lie algebra. Let's say, since everything is a K, since D is K equivariant. And this module contains crucial information for the representation for the G module X. Namely, we have a Vogan's conjecture. Which was proved by Huang and Pandđzi in 2002, which says that if X is an irreducible GK module with non-zero Dirac cohomology, then we know the infinitesimal character of X. So it's a sort of Kasselman-Osborn theorem for Dirac cohomology instead of Lie algebra cohomology. Okay, and now let me say a few words about the relation between theta correspondence and Dirac cohomology. So the question that we wanted to treat was the following. One. So fix an irreducible reductive dual pair G1 and G2. Choose P1 irreducible and unitary representation of G1 with non-zero Dirac cohomology. So the question was, what can we say about the Dirac cohomology the representation that we obtain if we consider the theta lifting of P1? Is it non-zero, for example? Okay, and let me state our results. Actually, I have to admit that I cheated a bit because actually, in this case, for complex groups, everything is fine. But there is a more general definition of theta correspondence where one has to lift everything from the symplectic group to the metaplectic group. But in this context, everything works fine. So the first theorem So the first theorem concerns the reductive dual pair of type 2. So we have GLM, GLN. And P1 is an irreducible unitary representation of G1 with non-zero Dirac cohomology. Then the theta lifting of P1 has non-zero Dirac cohomology as well. And actually, we can obtain some extra information. Actually, we can compute explicitly these Dirac cohomologies for P1 and for the theta correspondence of for the theta lifting of P1. That's for reductive dual pairs of type 2. Now we have a similar result for reductive dual pairs of type 1. So when G1 is an orthogonal group and G2 is a symplectic group, but in almost every case, the Dirac cohomology of the theta lifting of P1 is a 0, apart from some singular cases. So there is a difference between type 1 and type 2. And let me just state two important results that we used for the proofs of these theorems, and then I will finish. So our study was based on the following. Our proofs were based on the following results. The first one is due to Adams and Barbash. from 95. So roughly speaking, they explicitly gives the theta correspondence for complex reductive for complex reductive dual pairs. That was the first result that we used. And then the second one is due to, so it's due to Spyros Afentoulidis-Almpanis and Spyros donc Huang. That was from 2002, from 2022. And more or less, what they prove is that whenever P is an irreducible unitary representation of some group G plus some extra integrability conditions, its Dirac cohomology is non-zero. So its Dirac cohomology, I use P. Its Dirac cohomology is non-zero if and only if P is induced, is parabolically induced. So here we have a parabolic. From some representations which are important in representation theory of reductive groups, which they call it essentially unipotent representations. So they are some representations which can be considered as the fundamental bricks, the fundamental blocks of for the reducible representations of G. Here, yes, but probably it's not so important. I mean, we can, yeah, in any case, there are results concerning the infinitesimal characters and theta correspondence. I mean, we don't need the Dirac cohomology in this case too. Excuse me? The Dirac cohomology for? Being zero. Ah, for being zero. Yeah, yeah. In most of the cases, Dirac cohomology is zero. Yes. I mean, there are sporadic points where Dirac cohomology is non-zero. Yeah. For most of the cases, Dirac cohomology is zero. So if you want, I mean, we have Dirac series, which are irreducible unitary representations with non-zero Dirac cohomology and unitary dual. There is a big gap between these two sets.
Let's thank the speaker again. So it's not important.